Hi folks, we are back. Section 4.4.1, talking about model comparison and what's something called the Bayesian information criterion. So what we're going to do is we're going to use what we just learned in the previous section about the Laplace approximation to help us approximate the model evidence and decompose it into a likelihood term and a penalty on the complexity of our models. So it'll just give us another little tool to use to evaluate our models and pick amongst them. Although in real life you typically do still want to do cross-validation. Anyway, it's nice to see how, in theory, one could use what we've learned to come up with these, how they play with these model evidences and how to, evaluate our different models. Okay, so let's get going. So as well as approximating distribution, we can also obtain an approximation to the normalization constant, okay, Z. So remember, we've got 4.111. We have some function here. F of Z is, it's some distribution we're after, and we've modeled it here as some value at the peak times this kind of exponential term. Okay, so and our normalizing constant is going to be the integral over our unnormalized distribution. And so we've now approximated the distribution, and so we've got this peak term, and then we've got this Gaussian term, unnormalized Gaussian term, and from the standard results, we know that it comes out to this. So we have noted that the integrand is Gaussian and make use of the standard result for a normalized Gaussian distribution. Okay, so now we're going to be able to use this result to obtain an approximation to the model evidence, which plays a central role in Bayesian model comparison. Okay, so we're just going to effectively just look at what our model evidence looks like and plug in these values. So let's see how to do that. So consider a data set D and a set of models M sub I having parameters theta I. For each model, we define a likelihood function, which is depending on the parameters of the model and the model itself. If we introduce a prior over the parameters, then we are interested in computing the model evidence for the various models. So it's basically integrating over the parameters of the model, and thereby penalizing more complex models, right? Because the more complex models will always have a better likelihood, and so we want to essentially offset that with to be essentially balance that against the complexity, so that to avoid overfitting, basically. Okay, so from now on, we omit the conditioning on M sub I to keep the notation uncluttered. Okay, so what's the model evidence? So the probability of the data is, you integrate over the parameters. Okay, so now we're just going to essentially just map them one to one. So we're going to say our f of theta is this function right here, so this integrand, and z is going to be the model evidence, and we're just going to plug in this particular value, right? So we're exactly in that situation. Here is our f of z, and here is our capital Z, our normalizing constant. Okay, and so if we just take the logarithm of what shows up here, so let's just log, this would be the ln of f0. This is like the ln of 2 pi m over 2, and then this is the ln of 1 over a to the 1/2. So this is all just, we're just doing this one-to-one mapping. And notice that this is kind of the log likelihood for those parameters at the peak that we found, and then everything else here is kind of a complexity term. It's penalizing the complexity, and you can kind of see that because for example, things will kind of scale with the complexity of the data. So here is there'll be some term that's determined on m, the number of parameters you have. That's coming from here. This again, these parameters, if you assume this is a prior in your parameters, again, there'll be m parameters. So this will also kind of, be, I guess, like order of m times something. And then here, this will also, what will this look like? So this is going to be, and there's actually a problem on it in a second. Maybe we'll get onto it, but this will also be m times, something. So this will be a kind of a term that's kind of scaling with your, with the number of your, getting larger with the number of your parameters, and so it kind of suggests that's kind of a complexity term. So where theta map is the value of theta at the mode of the posterior distribution, just like what we needed, and A is the Hessian matrix of the second derivatives of the negative log posterior. All that's saying is just the second derivatives of this thing, basically. The first term on the right side of this represents the log likelihood evaluated using the optimized parameters. while the remaining 3 terms comprise the Occam factor, which penalizes model complexity. Now, if we assume that the Gaussian prior distribution over parameters is broad and that the Hessian has full rank, then we can approximate this guy right here very roughly using just this log likelihood minus a term where it's got, okay, it's increasing logarithmically with the data that you have, times m, which is going to be your the number of parameters. And this is what's called the Bayesian information criterion. And it compared to the AIC, I guess it penalizes model complexity more heavily. We can compare that. I haven't done the comparison, but that seems to be the case. And complexity measures such as AIC and BIC have the virtue of being easy to evaluate, but can also give misleading results. In particular, the assumption the Hessian matrix has full rank is often not valid, since many of the parameters are not well determined. And so later on we're going to find again use the Laplace approximation to come up with a better measure of the model complexity or of the model evidence. Yeah, so one thing I just wanted to mention here is, so basically what is this going to look like? So there's actually a good exercise, I think it's 4.23 on showing this. But basically the idea will be, like, where does this m ln n come from? That's going to come from A. And it's going to be because you're going to have, if we assume that these data points are going to be, independent, then this whole thing is going to be equal to, let's say this bit is going to equal to, the sum on ln of, p of di given theta map. And then this is going to be, approximately equal to n when you take and there's going to be a double derivative in there. And then it's going to be, something like, okay, so a bunch of derivatives, a bunch of, variances, up to sine. And then when you take the determinant, then the determinant of this is going to be equal to n times, let's say some theta to the m, and then when you take the log determinant, it'll be m times ln n blah blah. So the ln n is just reflecting the fact that you have n data points, and it's kind of blowing up, and the m is coming from the fact that you have m parameters. But anyway, it's a good exercise to look at. I think the main conceptual point here is, and I think it's a good one, despite the fact that we won't necessarily, if I want to evaluate model complexity, I have tried these information criteria. Typically, I find cross-validation is much more reliable, a bit more, obviously, compute intensive, more reliable. But nevertheless, I think it's kind of nice to see how these, how in simple cases, like you can even imagine, let's say my data is Gaussian. What does the Occam factor look like? And how do the various aspects of the model come in? So just very nice to see where that comes from. And basically, it's you have your model evidence, and now we're going to at least try to fit it with a Gaussian. And as soon as you do that, you get this split between the Occam factor and the log likelihood. This will always improve for more complicated models, but then you will get penalized. There will be a negative term showing up here, which will eventually penalize the very complicated models. So I think it's good to know about these. Try them out in your data. Have cross-validation always there, but just to see how they work, I think it's nice to kind of gain intuition as well. Good, so I think that's all I wanted to say about this chapter, and then we're going to go on to the next section, Bayesian logistic regression. We're going to use our new tools, our new approximations of complicated integrals to figure out, to apply them to logistic regression and integrate out the parameters that we come across there. So hopefully this was useful. Let me know if it was or wasn't in the comments, and I will see you in the next video. Bye.